Welcome everybody to this session on quantum computing. I'm very happy to host this session here in Singapore. Good morning from Singapore. Good evening in US and Europe. Thank you for staying up late to watch this. Before further ado, let me introduce my panelists briefly, and then I will pass it to them to say a few things about themselves and the place. So we have Professor Phillips, we have Professor Latorre, and Professor Gao. Could you please introduce yourselves to the audience? Bill.
Okay, my name is Bill Phillips. I work at the National Institute of Standards and Technology in the United States. That's our National Metrology Institute, and I'm also at the University of Maryland, and my research group is known for making gases and atoms incredibly cold. We operate with gases that are a few nano degrees above absolute zero. And with these atoms, we can make quantum devices that allow us to do some of the things that you need to do if you want to make a quantum computer. So that's how I got interested in quantum information.
Thank you, Bill. Jose?
Hi, everybody. I'm Jose Ignacio Latorre. I'm the current director of the CQT, the Center for Quantum Technologies in Singapore. And my research was initially in high energy physics, but then it turned into artificial intelligence and then quantum information.
Thank you, Jose.
And yeah, I'm Yvonne. I'm an assistant professor in the National University of Singapore and the principal investigator in the Center for Quantum Technologies. My work also, relates to what Bill said about something very cold, but a little bit hotter than nano degrees. We actually cool electrical circuits to about a few millidegrees above absolute zero, and we tease out their quantum properties and use that to build information processing parts and tools.
Thank you, Yvonne. And a few words about me. I'm also a quantum physicist, working in quantum computing here in Singapore. I'm a principal investigator in the Center for Quantum Technologies. And I'm also a professor on leave now from my home country, Greece. I also work on quantum algorithms and also implementations of quantum computing. And basically, what can you really build with a near-term quantum computer that hopefully will have some impact? So let's move on into the discussion. Let's start with Bill, maybe on this first question. Can you tell us a little bit in simple words, what is quantum computing and how does it work? What is all this about?
Okay. Well, let's begin with just a minute to say what quantum physics is or what quantum mechanics is. When you look at things at the level of atoms and molecules and electrons and nuclei, there's a different set of rules that govern the behavior of these kinds of things, and that's quantum mechanics. And the rules are a bit strange. We often say in ordinary life that you can't be in two places at the same time. But an electron can be in two places at the same time, and typically is in a lot more than two places at the same time. Now, how does this relate to quantum computing? Well, first of all, let's remind ourselves about ordinary computing, the kind of thing that allows us to see one another on this wonderful video chat. The information that makes all of this possible is being stored and transmitted and processed as digital information, as information that are either ones or zeros. But those ones or zeros are physical things. They might be a transistor that is on for one and off for zero. There might be a place on a magnetic disk that is magnetized in one direction for one and in another direction for zero. Physical things. And the power of that kind of information processing is that we are very sure that it is one thing or the other. In quantum information, we also have ones and zeros, but the physical things that represent those ones and zeros are quantum objects. Things like, for example, a single atom, or in some cases, a very small electrical circuit that behaves like a quantum object, even though it's bigger than a single atom. And the beauty and difficulty of this quantum information is that the zeros and ones are not necessarily firmly 0 or 1. Sometimes, if we work things right, they can be both 0 and 1 at the same time. Just as I mentioned that an electron is often in many places at one time, the state of an atom or the state of an electrical circuit can be in two different states at the same time.
Amazing.
Now, why is this a good thing? It sounds like a disaster, because if you measure it and it's in two things at the same time, when you measure it, you'll get one of those answers, but you won't be able to predict beforehand which answer you'll get. That sounds horrible. But the beauty is that if you have lots of these zeros and ones, these quantum zeros and ones, we call them qubits for quantum bits. If you have a lot of them, then it means that you can process many different things essentially at the same time. And certain kinds of problems become possible that are essentially impossible to do if you use an ordinary computer.
Thank you, Bill. That's really, really exciting. I know, a 3-minute review of quantum mechanics is a tough job for everybody, but I think it was very, very illuminating. Let's talk a little bit on how do we got here? How quantum computers became a little bit the theme of the day, and we read articles on Economist and here and there. It's not only in physics anymore, but where did the journey start? I would like to discuss a little bit how basic science and basic research in quantum physics led us to here, and how do these qubits get let's say implemented or materialized in the real laboratories. I would like to start with Yvonne on this. Mm-hmm. Bill mentioned a little bit about small things and cold things. Can you tell us about your opinion on this? How do we build these things?
Yeah, absolutely. I think Bill already mentioned that electrical circuits, if we build them and control them in a certain way, can also exhibit good quantum properties and behavior that we can use for quantum computing processes. So that's the field called superconducting circuits or circuit quantum electrodynamics. So the special thing about this is we use materials that are superconducting, which is essentially saying that they can conduct electricity at low temperatures without causing any dissipation. So that's great, because then we can really minimize the noise that tends to drown out the quantum properties of our nicely designed system. And these circuits are actually quite intuitive if we think about it in the context of classical computers, which are essentially electrical components pieced together in a clever way, right? So quantum circuits are effectively, 3 types of elements, which are inductors, capacitors, and this thing called Josephson junctions, which actually, was one of the main discoveries in the 60s in this field of physics. And Brian Josephson actually won the Nobel Prize in 1973. So, all of these very fundamental physics in superconductivity, which was another topic for the Nobel Prize, condensed matter physics, Josephson effects actually all tie in together in the field of quantum circuits. And we now put these components together in a specific way to make, in some sense, bespoke or on-demand quantum platforms to do gates, to do information processing, and in the future to compute useful things for other applications. Thank you,
Yvonne. That was very, very nice. So we have tiny and very cold quantum circuit built from superconductors. So that's kind of a little bit close to what we have these days, so we can imagine the translation, but in a quantum and a superconducting way. But they're also very exotic type of processors that they don't really look like chips, made from atoms and ions, right? So Bill, can you tell us a little bit about them and how we got here? I mean, as Yvonne said, there's definitely probably a dozen of Nobel Prizes in laser physics and including yours the last 20 years in this area. So could you elaborate on this?
Well, quantum mechanics started with people trying to understand atoms. So it's not surprising that atoms also are one of the platforms on which we do quantum information. So instead of having circuits that are little microscopic circuits, we have even more microscopic objects, which are atoms themselves. The size of an atom is a fraction of a nanometer, whereas some of these electrical circuits could even be as big as a millimeter, but usually you try to make them smaller than that. But one of the advantages of the atoms is that because they're so small, we can put a lot of them together very close. But one of the disadvantages is that they're very close, and we need to manipulate them individually. So this is one of the interesting features about these different kinds of platforms for quantum information is that each of them have their own advantages and disadvantages. The advantages of the superconductors, or one of the advantages, is that it's easy to isolate each circuit and to manipulate it individually. The advantage of the atoms is that they're much better isolated from the environment, which is one of the things that you have to do if you want to make a good quantum computer. So let me just say a minute about what is it in the atom that is carrying the information. Well, one of the images we often have for an atom is that we've got a nucleus, and then we have an electron, and the electron is going around the atom. Now, that's a pretty bad picture of what an atom is really like, but it's good enough for this idea. The nucleus often has a spin, so I'm going to indicate that by putting my thumb up and imagining that the nucleus is spinning in the direction of my fingers. Okay. Now the electron also has a spin. Let's imagine that it's spinning in the direction of my fingers. Now, just to assure you that this is a really stupid model, I'm talking about this electron spinning around, but the size of the electron is exactly 0. So think about that for a little while. How does something spin that has a size of 0? Well, I have no answer for that, but I'm going to talk about it anyway. So the relative orientation of the spin of the nucleus and the spin of the electron is one of the things that determines the energy of the atom. And if I turn over, have the electron spinning in the opposite direction, that changes the energy. So I can make this be 1 and this be 0. And somehow, in the strange world of quantum mechanics, it can be both things at the same time. And that's how it works for atoms. With superconducting electronics, it's a little different.
Thank you, Bill. And you know, we started from hardware and how we physically build these things and how they look like. And as we just noticed, they definitely look very different than current computers. But I would like to shift to what can they do, these machines, if we build them at some point. And we do have them in a prototype, maybe experimental version, but what can they do? And I would like to invite Jose Ignacio to talk a little bit about the use cases of quantum computing and, you know, in the broader sense, what kind of problems could they attack that maybe are difficult these days? Do you tell us?
Okay, Dimitris, thank you. I think that we have to take this question in two contexts. One is a more historical one, just to understand that we are living the infancy of quantum mechanics. I mean, it's a newborn baby. We are just discovering the rules, and we are even disputing whether we understand them or not, or what is our way of manipulating them. And then in this context, you can see the 20th century as a fantastic century. You know, in 1900 we discovered quantum mechanics. 25, 26 we had the Schrödinger equation. In the 30s the postulates, and then we started to use this knowledge to create something for us, some instruments. Like in 47 we had the transistor, or then the lasers in the second half of the century. So we can understand the recent progress on quantum computation because we do have instruments which are themselves quantum, and they have refined our control of matter. So this is why we're going to the next step. So in this sense, because we are living this infancy, it is still extremely premature to know what we can do with a quantum computer. Now, the second way of answering the question is what's going on. So all the research which is going on, we have a lot of people doing quantum algorithms, and we have some success, like the algorithm by Peter Shor that allows for factorization of large numbers in an efficient way. That is, that the number of operations is only polynomial as the size of the system. Or we have a Grover algorithm, which is finding one item in a database with a square root advantage. So those are success stories. But in general, we are looking for something more ambitious. We want to have end users for our technologies. We would love to say that we have breakthroughs in artificial intelligence, in quantum chemistry, or how we deal with finance. But I would say, in my opinion, that we are still far from understanding the deep progress that can be made with a quantum computer. It would be a little bit of arrogant from the humanity point of view, no? Again, to claim that we are on the verge of solving dramatic problems. I think a lot of research is needed, and I hope many young people listen to that and they will join us.
Yeah, definitely. It's thanks, Jose Ignacio. It's an exciting journey. It's in the early stages, and it's I guess from what you say, it's like asking the people that discovered the transistor to predict the iPhone or something. So nobody could have seen it, but it was probably going to be even more exciting than that. So I think definitely for the young generation, it's the next few decades will be extremely exciting.
But you know, Demetrius,
yes,
I'm thinking that some of the things that you do are perhaps among the really exciting problems that we're working on now. You are interested in quantum simulation. And while we may be a long way away from factoring numbers, we may not be so far away from quantum simulation. Maybe you should say a few words about that.
Sure, thanks, Bill. Indeed, quantum simulators are, let's say, analog or the small brothers of quantum computers in a sense, but they are pretty cool in certain problems. So they are specially designed quantum computers that can do one thing or two things, but pretty well, like understanding, for example, complex interactions in materials, and figuring out whether a material is a conductor or an insulator, or even hopefully understand superconductivity a bit more. And you know, the holy grail is to go to room temperature. Or there are also other cases, and this including works that you guys are doing in the general condensed matter material science and chemistry. I think, you know, I see some hope in doing some chemistry calculations reasonably well, which are very tough for classical computers. Again, using electronic and fermionic systems, which they are close to what we're trying to understand. As Feynman has said, real quantum systems are very hard to simulate in classical computers. Why don't you just take another quantum system that you can manipulate better and you can control better and trying to understand that and simulate that? And that's what the quantum simulator is. So hopefully that will happen soon. Let's move to the next question. Let's talk a little bit about, because this is quantum computing is not only about computing or simulators. There's also other sectors and pillars, as we call them. There is communication, and there is quantum sensors. And let's talk a little bit about those areas as well. What's happening in these parts, and what's the state of the art, and what can they do? Maybe we can start with Bill on tell us a little bit about quantum sensors.
Okay. So there's a lot of different kinds of quantum sensors, but I think the thing that is particularly exciting today is to have sensors that have what we call a quantum advantage. So let me give an example. Let's imagine that I'm trying to make an atomic clock. Atomic clocks are the time standards for the world. Atomic clocks are what tell us how long a second is. That allow us to compare the frequencies of different kinds of physical phenomena. And the way they work is they use the intrinsic frequencies of individual atoms as the tickers of the atomic clock. Now, there are uncertainties with all of these things. You have only a certain amount of time to look at them. When you measure them, there are measurement uncertainties. And so what you like to do is to have lots and lots of them so you can average together the results of all of these many different atoms. That would be a typical thing you would do in an atomic clock. And if you don't do anything special, and by special I mean quantum, then the more atoms you have, the better your result is, and the result improves like the square root of the number of atoms. But quantum mechanics tells us that we could do better. If we do something special to the atoms, and that special thing is what we call entanglement, and maybe we'll talk a little bit more about what that means. But if we could entangle the atoms together in a particular way, then when we have more atoms, we can have it improve like the number of atoms instead of like the square root of the number of atoms. And you can see that even for a modest number of atoms, that could be a huge advantage. If I had 100 atoms, instead of improving the performance by a factor of 10, I could imagine improving the performance by a factor of 100. Well, we're just beginning to do this sort of thing with atomic clocks, and we're thinking about doing it with other kinds of quantum sensors. But that's one example of how you could get a quantum advantage from a sensor. In this case, a sensor of time frequency.
Yeah, this is quantum metrology. Yeah, calculating time, and just to give a bit of a scale, what's the best we can do now globally? 1 in 10 to the 18th, or something like that.
Exactly.
So we lose
exactly the best
every
clocks are
in the age of the universe.
Yeah, the best clocks are part in 10 to the 18th, but we're expecting that in the future, with some of these tricks, that we can go to a part in 10 to the 20th. That is sort of on the horizon.
Amazing. And
that would be 1 second in 100 times the age of the universe.
That's a really cool clock.
And it's not just cool scientifically, right? It has very direct applications like better GPS and things like that. And, you know, it has real impacts as well. Not just that a scientist wants to get the last digit, right?
Exactly. We need to be able to calculate time for many applications, and we want to be able to do it accurately. And in the sensors, maybe Jose Ignacio can say a few more things on sensors, and if she wants to add something on the sensing or the communication, can you?
Sure. Well, let me bring another example. I think people would love to listen to examples. So maybe one which I love is that we are doing accelerometers, for instance, which are amazing. Recently, we can trap mesoscopic particles with quantum techniques. And we can even make levitate on top of superconducting currents, and then measure the modifications of the position of the particle through the magnetic influence on NV centers on nanodiamonds. So it's like a science fiction movie when you listen to a talk. And it is simply a success, again, of humanity, I would like to say that. But then for quantum communication, which I think is very relevant, not only for ourselves in science, but for the economy of the countries. So because there is a threat from quantum computers to break classical cryptography. As we said, we have an algorithm that would factor numbers, and this is at the core of our present cryptography. So we need the solution, and it turns out that quantum mechanics provides the problem for classical cryptography and also the solution for classical cryptography, which is quantum cryptography. So it looks as if we had to, prepare the whole thing. We have contrived everything, so that we substitute the economy of communications. So the basic idea is that we use the qubits, typically with photons, implemented on quantum properties of photons to communicate, to send them from one place to the other. And the main challenges nowadays is to have ground communication between different sites, and also satellite communication. And the present status is that there is an effort in both. I will bring Singapore here into the game.
Yeah, yes.
We have both projects to make the island quantum ready for quantum cryptography, and also sending nano satellites that communicate with the Earth using entanglement, by the way, distributing entangled pairs. So again, this is like a science fiction movie. Okay, these ideas of deploying entanglement, not on a clock, as Bill was saying, no, that you entangle the particles there and you measure there. No, now the entangled particles are thousands of kilometers apart, and they entitle us to do secret cryptography. So let me say that not only we have quantum computation, quantum simulation, but sensing is manifold. There are very many things going on. And on top, we have quantum communications.
Right.
So it's really a second wave of quantum technologies coming over the planet.
Right.
So it's very spectacular.
Thank you, Jose. I'm a little bit worried with time, so we'll have to move a little bit faster. It's an excellent conversation, but I would like to keep some time for the questions. Let me take the last bit of your last sentence, Jose Ignacio, just to clarify, as you said, that now we're living the second quantum revolution. I mean, Bill made a nice introduction on the first kind of early discoveries of quantum physics and how we got the technology of the 20th century, the second half of 20th century, due to the discoveries in the early 20th century. But now we're going on the second, quantum technology 2.0, and where the information itself is quantized, and we are looking at things in a very different way and having these three different possible new routes in communication, sensing, and computing. So let's move a little bit to the this is the, as they say, the $1 billion or the $1 million question. What is the bottleneck, you see? Like, what do you think will it's one of the major hurdles in this journey? I mean, it's exciting. It has a lot of basic science. It has a lot of potential disruptive type of applications. But where would you see the challenges lying ahead? So, Bill?
Well, there's a number of different challenges, but one of the most important ones is what's known as decoherence. This is what Yvonne alluded to in how we have to protect our quantum objects from being scrambled, being messed up by the environment. This idea that a quantum system can be in two states at the same time will only be true if we isolate the quantum system from the environment. If we allow it to be affected by all the noise in the environment, then it won't be in both states at the same time. It will be in one state or the other. We just won't know which. And there's a huge difference between being in both states at the same time and being in one state or the other. And that difference is what's known as decoherence. And every quantum system is subject to that process of decoherence, of messing up this wonderful feature of what is called superposition in quantum mechanics. Now, what do we do? Well, there's two things we can do. One is to isolate the system from the environment, to improve the quality of the system so that it doesn't suffer from these things. And I know that Yvonne used to work in the group at Yale with Rob Shulkoff, and over the years, they kept making it better and better and better. And that's been one of the wonderful results of just really, really hard work on superconducting systems. But it's never enough. And so there's something else that has to be done. And that something else is a wonderful trick called error correction. And what it means is that when the quantum system begins to suffer from this decoherence, we can fix it. And the way we fix it is by having not just one qubit holding the information, but a lot of qubits. And because the information is distributed among all of these qubits, we can figure out what's gone wrong without reading out the information from the qubit. This is one of the great difficulties of quantum information, is that until the end, we must not know what the value of a qubit is. So we have to avoid knowing what it is, but we have to somehow figure out what went wrong. Well, there's a way of doing that, and it's called quantum error correction. And we're just beginning to implement this quantum error correction in real systems like the ones that Yvonne is working on. So that's one of the things that I would say is a great challenge of quantum information, is how do we deal with decoherence? How do we make quantum error correction work so that it really fixes things? So far, we've just begun to play with quantum error correction. We haven't really developed it enough that it actually fixes things so that we can do a really long calculation. But I'd love to hear what Yvonne has to say about it too.
Maybe Yvonne or Jose Ignacio can briefly comment as well.
Yeah, I think Bill already really outlined the need for quantum error correction, and I think one challenge, as as we are working on this topic, we see is that very often we have to fight against two constraints. One is decoherence, but at the same time, we still want good and fast control of the system, right? If we isolate it so well that we can never talk to it, then it's essentially a useless quantum system just floating in empty space doing nothing, right? So balancing these two constraints at the same time in a single hardware can be very challenging. It also adds the complexity of doing quantum error correction, because as Bill mentioned, we're distributing one qubit into many others, so that means it adds the overhead and complexity of controlling a lot more at the same time, quickly and coherently without introducing additional noise. So definitely in this on this front, there's a lot more to be done in just understanding this better, and not just in terms of the quantum part as well. We also need to look into the electronics that we have. How quickly can we do things like feedback or stabilization through clever classical algorithms, or filtering of the information for error correction after the quantum process is done, to really enhance this technique of preserving the information and fighting against the noise.
Thank you, Yvonne. And let me close this question with discussing a little bit the challenges in the theory side and algorithms, and maybe I can just mention that I think I would like Jose Ignacio's view here as well. It's very exciting what's happening recently. I mean, the early algorithms, as Jose mentioned, Grover and Shor is one way to do quantum computing. But as time goes by and the field grows and more people come in, and this is very important for the young people, we see new angles like machine learning and quantum getting together. Then we see some sort of different approaches in approximate methods, in AI and quantum, in variational approaches. Would you like to say a few things there? Okay.
Yeah, I think we are learning how to use a quantum device in an intelligent way, which is not plainly naive algorithm. So we can think of a quantum machine as a machine that explores a vast space that we call the Hilbert space. So we are understanding that we can design new kind of algorithms that simply try to explore that gigantic space with a machine called a quantum computer. And this is something that was not possible, or it is not possible with classical means. So this is great. But let me add let me just add a little comment, because I guess that many of the people in the audience are not scientists or may not be in quantum mechanics. So there is a concern of when all these things will come to industry. Many people ask, and when will we have a quantum computer at home or things like that? So here I want very fast to say two things. The first is that as scientists, we have to protect ourselves against the quantum hype, that the people trying to claim that everything will be changed by this. No, to write a letter, you don't need a quantum computer. You can do it with a pencil, actually. You don't even need a classical computer. You can write it by hand. So it's only for certain tasks that we may take advantage of all this amazing knowledge that we are developing.
Right.
But then on top, it has to be profitable for the companies. Otherwise, they would not come there. And this is, for me, a challenge and a bottleneck. So that not necessarily anything we produce in the lab will translate immediately in an advance of our industries. So it will take time to refine. This said, it's unavoidable. There is no way anybody should think that quantum technologies will not permeate our economy as they have been doing for the last century. And we are just not living a special moment, I think, in the history of humanity. We are just, it's our time, that's it. But it is unstoppable. Yet, it's not trivial, okay? So we have to deal with this duality of the amazing feeling of what we're discovering and down-to-earth understanding that getting things done out of that is not immediate and not trivial.
Right. Thank you, Jose. Let me just make one comment on that. Sometimes I like making the analogy to the early times of classical computers or normal computers. So if we go back 60 years in the 1940s and the first machines, the ENIAC in 1948, 1949, it was built for very specific applications, at that time military applications, calculating projectile trajectories, because that was what was tough to do, and you needed, a whole army of people to do the differential equations, and it was unforeseen that it could be used for anything else at that time. And even there's a famous quote that there's a market for 5 computers in the world that came up later on. I think from IBM even, or that's quite funny. But I would like to also stress the point that blue sky research, and as we call it, basic research, is extremely important. And now we are living through a period where a lot of companies have come in big or small, from the biggest ones maybe in the planet to even tiny startups from students and postdocs and some of our colleagues venturing out to the business world via either computing or sensing, and this is exciting times. So we have to be able to balance the expectations to the real science. So we are almost towards the end of this part. Before we get into the questions from the audience, let's just say a few things about the quantum initiatives globally. I already stated a bit about the companies and also the big programs, and also in Singapore. So let me start from Bill, like what's happening in the US in the field, both publicly and privately, and then we can move to.
Well, you may have heard that recently in the United States, the federal government has decided to devote a lot of money, or at least it seems like a lot of money to me. There's a joke that says $1 billion here, $1 billion there. Pretty soon you're talking real money. So the government has decided to devote some billions of dollars to study quantum information. And in addition, a number of private companies like Google and IBM have decided to devote a more modest amount of money. And we have a lot of startup companies that are relatively small that are devoting money to this. So a lot of things are happening. One of the things that I would like to emphasize, and it may be as much a dream as it is an opinion, is that I don't see quantum information and bringing quantum information into reality as being a race between people in different laboratories and in different countries. I see it more as being building a barn where a lot of people get together and make something happen that no individual could do on their own. We're building this barn all over the world. And of course, the reason that works is because we have communication like this that allows us to know almost instantly what our colleagues are doing in other countries. And so for me, it's a wonderful adventure, but it's an adventure that is shared with the entire world.
Thank you, Bill. This is a very good point. Being open and stay in communication and share scientific knowledge is the way to advance. And the challenges are so high from what we just discussed that's the only way to go. And definitely science to stay out of any geopolitics or all these other things that are not relevant if we wanted to proceed. But let's comment a little bit on the local efforts here in Asia and Singapore. Maybe Jose can say a few things.
Yeah, well, just to bring a less positive point of view, I think that the stakes at quantum technologies are so high that more and more we will see proprietary solutions developed and, in countries. And I'm sad because I'm obviously an open source person, but I see more and more companies and countries, keeping secret research.
So we're being very romantic with Bill, and you bring it down to earth now.
Yeah, well, no. I agree completely. What we have is the result of collaboration, not of secrets. But it's a fact that the more things are progressing, the more you see other ways of proceeding appearing. Okay. For Singapore, let me again be very fast. Quantum technologies have been detected as one of the fields where investment will be done in the next 5 years. And in particular, there is a program called Quantum Engineering Program, which is to bring the island to a higher level and to increase the collaboration between all the parties. And this is just starting, and we are articulating it. It has been articulated by all the stakeholders in the country. So I think it's an example of, let me put it in this way. You have USA on one side as a leading country. You have China doing enormous progress. You have the European Union, but then there are these other countries like Israel, like Korea, like Singapore, like Australia, that we are doing, I think, very well, okay? And we should be trying to collaborate as much as possible with all the other countries and to guarantee that we are not left behind.
Okay. I think we're close to the end of this part, so let's move to the Q&A. We have quite a few questions from the audience and the scholars watching this from different countries. Let me start from Thailand. There's somebody from Mahidol University, Kajana. We can bring her online. Kajana, are you there? Or I'll ask the question. So the question is.
Sorry.
Can you hear us, Kajana?
Okay, can you hear me well?
Yes, please, go ahead, ask your question.
Okay, sorry, I'm excited. My name is Kajana from Thailand.
We're surprised you, that's okay, go ahead.
Yeah, I'm very glad to be here, and my question is, if we can represent electron in form of qubit, can we better represent electron behavior and better can make the quantum calculation in physics and chemistry more accurate and efficient?
So the question is how we can calculate physics and chemistry better using quantum computers. Maybe Jose Ignacio can say a few things on this.
Well, that's a basic idea that we take particles such as the electron and we understand their properties and we make an abstraction. In a particular case, maybe the spin is the only relevant quantum number characterizing an electron. And that is for us a qubit, okay, what we call a logical qubit. And then we can understand the laws obeyed by this quantum qubit. So eventually it's an electron, but we treat it as I think this is the idea of the question. So if we make the abstraction of the physical properties into a qubit, can we use quantum computers to analyze the properties of this electron? And the answer is certainly yes. And that is, for instance, what we try to do in quantum simulation and in quantum chemistry, to give examples. There is a lot of ingenuity in how to do that, and it may depend on the particular problem that you are addressing, and this is why this is a field of research. So that's why there are papers all the time trying to use quantum computers to understand better a quantum system, which is a real quantum system, by making the abstraction of the quantum properties in terms of the qubits.
Thank you, Jose. Let's go to another question now from Dominica, if she's there, or he or she. Hello.
Hear me?
So please ask your question. Tell us where are you from? You said Slovakia, MIT. Are you in Slovakia or at MIT now?
Yeah, so I'm in Slovakia right now. I'm flying to MIT hopefully soon.
Great. So it's my part of the world. I'm great. Yeah. So go ahead, ask your question.
So thank you. So my question is related to the hardware part of quantum computing. So people around the world seem to be competing or collaborating, I should say, in some sense to come up with, what the best hardware for quantum computing is. So, there's trapped ions, there's superconducting qubits, there's neutral atoms. So I'd be interested to hear what your opinion on this is, whether you think that, there will be this one hardware that it's going to take over all the quantum computers in the world, or whether you think that there's potential for these different platforms to be combined in some way, or even for new platforms to come in the near future. Thank you.
So who wants to take that? Any of you?
I can take that first, and then maybe if Bill have things to add, we can both comment. So I think that's a great question. I think we all think about that a lot as hardware builders. So my personal opinion is that we don't really know what form the quantum computer hardware will take exactly in its final incarnation. And each of these hardwares have their own advantages and disadvantages. So if I were to guess, most likely that in the future we might develop some sort of crossover things where the memory element can be implemented with, physical systems that are extremely good at storing information for long periods of time, but the actively computing part could be built with things like circuits that are very easy to control and do good gates on. So it might look very different from what we see as quantum computer prototypes right now. But I think the technologies we're building will all, go into powering that eventual platform that we end up choosing.
Right. Thank you, Yvonne. So if anybody wants to add anything, or should we move to the next question? We have a big list. Go ahead, Bill.
Well, I'll just add just a moment. For one thing, it's good to see you again, Dominica. We were in an earlier discussion earlier today. I agree very much with what Yvonne said. I wanted to add another point. For her particular area, which is superconducting quantum computing, if someone asked me about 15 years ago whether I thought this was going to be a good platform, I would have said absolutely not. The decoherence is much too high. There's no way this is ever going to make a good quantum computer. And now it's one of the most competitive platforms for doing quantum computing. So what that tells us is that things that we can't easily foresee may completely change what we think is a good way of making a quantum computer. And Yvonne made a very good point as well, that you might very well want a hybrid quantum computer where memory is atoms, because they can be free of decoherence, and processing is superconducting circuits because they can be very fast. And then the thing that's really going to be crucial is to have something that translates quantum information from one platform to another. And we are very much in need of having good transducers of quantum information. So that's going to be an important area of research in the near future.
Right. Thank you. Let's go to another one on this side of the world. Thank you, Dominica. From Chinese / Waseda, he's at Japan, Waseda University, Ji Chao. And this is I think it's an interesting question that can clarify a few things. Can you hear us, Zikao? Can you come in? No, he's not there. So I'll ask the question. The question is he coming in? This is all live, as you can see. We're picking people up from the question and put them online. And I think, hello, are you there?
Hi. Yes.
You get to ask a question to this excellent panel. You got the lottery, so ask your question.
Hi, people. My name is Zhao.
Right.
I'm Chinese but I'm living in Japan right now. So my question is related to using quantum computers to use AI. Sorry. Can you hear me?
Yeah. We can hear you. Go ahead.
Yeah. So yeah, just any way to boost significantly to for faster AIs or more sophisticated AIs. That's it.
That's a very good question in the sense that, AI does everything these days, right? We hear it everywhere. Countries are investing. Everybody's doing AI. It's the coolest world, maybe after quantum, or I don't know which one is leading. So can we combine both? And what's going on there? So what's the reality? What's the hype? And maybe anybody, Jose or Bill or anybody who wants to take the question.
Even yourself, Dimitris, no? We work on this.
Okay, I can take the question. So AI can do amazing things, and it's definitely a significant improvement from the way we program computers in the past. They mimic learning processes in a different way, and that allow us to, do many things like checking for cancer in an X-ray even better than a trained surgeon after 20 years. If you saw the AI enough X-rays, it will tell you that the next thing is a tumor, a good or a bad one. However, the processing power is a bottleneck, and this work, quantum computers could maybe help. These days, to train a neural network, we use these massive data centers that produce a lot of heat. They can take as much electricity as a small town, and because that's the way that computing works. So if we could have faster processors, and where quantum is coming, this is one of the possible promises. This could definitely be enhanced. But there is also different ways to do quantum machine learning, which is not just enhancing the speed, is exploiting the uses and the properties of quantum mechanics, this probabilistic nature, and figuring out these exotic states and figuring out exotic patterns in data. That's another thing that we didn't see coming and is being building up. So there could be definitely possibilities if we get there. It's still the early journey. The algorithms are coming. We do design algorithms, and we see very different things that can work very fast, quadratically fast, or even exponentially faster, and the hardware needs to catch up. Okay, there's how much time do we have? Okay, we have 5 minutes. Okay, so let's see. So there's another one on this line on precision medicine. I think and healthcare industry, how quantum computers or quantum sensors can improve that. This is from a Chinese Academy of Science, a student or a scholar there. Does anybody wants to say a few words, brief words on this, how quantum could help that? I think we mentioned a bit on sensors, right? We mentioned that you could build highly, maybe Bill can tell us a bit about the sensors and possible things in medicine. And
well, I don't know much about medicine, but one of the things that popped into my mind is that one of the dreams of quantum computing is to use it for drug design.
Exactly.
So because of the possibilities that you may be able to do quantum chemistry calculations using quantum computers, you may be able to design new kinds of drugs using the computer to predict the action of the drug without having to develop the drug and then see if it actually works on people. This is what is already done, but with classical computers, and the results are not always as good as one would hope. The dream is that a quantum computer can do this better, faster, and so maybe new kinds of drugs. I think it's a speculative idea, but it's one of our dreams. Yes,
that's very, very, very good. Thanks, Bill. This is definitely and very, very timely as well. We're living through a pandemic, and processing and designing vaccines and figuring out brings a lot of different disciplines, including chemistry, better chemistry, but also better processing of data, machine learning and AI, what we discussed earlier. So quantum would probably have an impact on that at some point in the future. We are almost out of time. I will just do one last question, a last kind of wrap up, especially in this audience of young scholars, the new minds and the future of our kind of society and science in a sense. What would you advise this audience we have now? What would you recommend if they are excited to do something on quantum? How can somebody enter the field? Like, let's say, as a student or even a high school or a student or a university, but is not already involved in quantum stuff. What would you advise them to do?
I think that this is not so different from any other disciplines. Really, it's learn. Explore things as much as possible at the early stage, and also like build a solid foundation in physics, as you've heard from all of us, that all of these technologies are rooted in the fundamental understandings of various physical principles. So there's no running away from that. So if this is an area you're interested in, it's not necessary that you need to start reading a quantum information textbook right now, but rather, start with basic quantum mechanics, acquire a good foundation in that, and then you can pretty much explore any other quantum technologies using that knowledge and that foundation. Right.
So if somebody is from, let's say, is not a physicist, is not doing a physics degree, but is an engineering or a mathematician or plans to to do that. So how would sciences? Let me give my personal take here. We split sciences in boxes and we say physics, engineering, mathematics, and so on. But I think as time goes by, we see that these things are more and more integrated. And some universities are picking that up, especially the quantum information, I think, enhance this kind of interdisciplinary approach. And we are seeing a few master degrees, we're seeing a few even bachelor's degrees in quantum engineering, in quantum technologies. And I think this is very exciting, and I would like to highlight that this is a very interdisciplinary thing. Physics is definitely the core. You need to understand what's going on, but there is programming, there is machine learning, there is algorithm design, there is mathematics that come in. It's very varied, and I think can fit any taste according to what somebody likes to do most. So I hope there will be more actually in this direction, that the universities will do more programs on this. We do have programs in Singapore to highlight that. We have a PhD program here in the Center for Quantum Technologies. There's quite a few groups looking for students. If anybody is interested, go to our website and check and write to the right PIs. I think, are we okay with time? Okay, so I think it's time to wrap up from what it seems. Thank you very much, everybody. Thank you for joining from different time zones. I know, I hope it was an exciting discussion for everybody and the audience. And take care and stay safe.
Bye.
Bye-bye. Thank you, everyone, for being here.
Bye.